So in this video, we will introduce non-symmetric matrices. However, non-symmetric matrices bring to focus eigenvalues and eigenvectors. So let's actually zoom in and look at eigenvalues and eigenvectors. So they are best understood in a dynamic system. So what we have in this visual is actually a discrete phase space. Every point is a position vector x1 comma x2, and we apply the transformation using the matrix multiplication from the left. The matrix is A, which is a diagonal matrix in this visual. The next position vector is arrived by that transformation. So that is what this phase space evolution is showing. When the diagonal values are greater than 1 along the particular direction influenced by that diagonal, there will be growth. If it is less than 1, it will shrink. In this particular example, both the values are greater than 1, and we are seeing that the position vectors are evolving outwards. So it is similar to basically in the previous visuals we have seen a circle transform. So in this case, if we had a unit circle that's becoming a larger circle, both the diagonals are exactly equal. So along all the directions, the stretch factor is exactly the same. So there are also some specific points which are shown as highlight. So that will become more useful to see when there is a difference in the two diagonal values. Here both the diagonal values are the same. So we are seeing all these points traveling along their original direction. The directions changed for none of these vectors. So in the next visual, both the diagonals are still the same, but basically they are lesser than 1. We are seeing that the position vectors are evolving towards the origin. There is a compression. If we had a unit circle, that is actually becoming a smaller circle. Yeah, so in this example, basically the diagonal values are different. One of them is 1.01, sigma 1 is 1.01 and sigma 2 is 0.99. So along one direction we have an expansion, it is greater than 1, and along another direction it is shrinking. So let's actually look at the visual. That is what we are seeing, the trajectory is evolving as well. So the other interesting thing to introduce is the rotation directions. The orange dotted line and the green dotted line are the rotations by the 30 degree. So we are actually doing this rotate by 30 degrees, transform using the diagonal matrix, and then rotate back by 30 degrees. We did have this rotation component in the previous visuals also. The diagonals being exactly the same, cast the matrix A to also be a diagonal matrix. But however, when the diagonals are different, we actually have got the symmetric matrix here. So the other thing to observe is that there are these highlighted position vectors and their trajectory, like especially the white dots, the white position vectors and the yellow. So they are traveling along the orange respective lines, the orange dotted line and the green dotted line. That is, their direction did not change. The yellow dotted line is expanding, it's flying out. The white dotted line is flowing towards the origin. So that corresponds to sigma 2, which is compressing. So those are the observations that we have. So the main point here is that basically there are these special directions. So that direction is actually called as eigenvectors. Vectors on those lines stay on those lines, unlike the other vectors that are shown also. Other highlighted vectors are changing direction, but the vectors on these two lines, even after the transformations, they are actually staying on the line. So those are our eigenvectors. So the rotation direction and the eigenvector direction are exactly the same when it comes to symmetric matrices. So now what we have here is a non-symmetric matrix. A transpose is not equal to A. The diagonals actually are showing sigma 1 as 1.09 and sigma 2 as 0.91. So there is one of those directions is having a stretching and another direction is having a compression like before. But in addition, there is one more observation that the rotate and rotate back are having different angles here. 28 degrees and minus 30 degrees. I will call this angle a residual angle. I see a residual angle of minus 20 degrees. We rotated performed a transformation, but we did not rotate back by the same amount. So let's actually go look at what happens to this visual. The sigma values are a bit higher, so this moves a bit faster. So the first observation is the white dot and the yellow dot are no longer staying on the orange dotted line and the green dotted line here. The orange dotted line and the green dotted line corresponds to R28, the rotation by 28 degrees in this example. So the singular value decomposition, the orthogonal basis of the vector V. So that is a direction which is not getting preserved. Vectors on that direction are changing the direction after transformation. However, actually, as we see it progress, we are actually able to see that at least in this example, the arrows seem to be converging along a different direction, which is not the same as the orange dotted line and the green dotted line. Eigenvector directions are the directions on which if you pick a vector, apply the transformation, the resultant vector stays on the same line. So here is another non-symmetric matrix. Here the residual angle, what I'm calling as residual angle, is minus 7 degrees. That is basically the V vector has a rotation of 23 and the U vector has a minus 30. So this is carefully chosen to show another interesting pattern. So let's run this visual to see what happens. So what we are seeing is a spiraling behavior. There is clearly rotation. So unlike the previous visual, which was also a non-symmetric matrix, we don't see this converging into a particular direction, right? There isn't a direction that we can see where any of these vectors are converging. So that is one of the interesting thing about this carefully chosen non-symmetric matrix here. So we introduced the notion of eigenvectors. In this particular, for this matrix also, there is actually an eigenvector, but it is in the complex plane. Whenever there is rotations involved, there is complex planes and vice versa. So in the next video, we will look at artificial neural networks. We have very simplified example. We will actually also get a bit of an understanding of what NumPy is at a beginner level and use NumPy to actually solve that simple exercise that we will take up.